method and part 2, which is a more advanced method. So depending on your level of interest or expertise, you can pick either way. So I'm going to show both versions today. All right, so just a refresher on the viability assay. So you have your live dead cells. The cell on the left in circle is live cell. Its membrane is intact. And the dead cell on the right, the membrane is leaky. It's got holes in it. So we can use those piece of knowledge to take advantage of it and use fluorescent dyes to label those cells. But the one thing is we need to have a common dye between the two, and that is going to be our nuclear staining. So we can use the viability stains of calcium AM for the live stain, PI, propydium iodide, for the dead stain, and the Hoechst for the nuclei, because the calcium AM only moves into live metabolizing cells. PI will only go into dead leaky cells, and Hoechst will stain everything. So this is a little cartoon of what's going on. And here are some images of the live dead and the live total cell staining. All right, so just a general overview of the workflow for the assay, the viability assay. On day 1 of your experiment, you're going to want to plate your cells depending on the plate type. So if you're doing a 96 or a 384 well, the number will vary, and that also will vary according to how long your treatment is. If it's a 4-hour versus a 24-hour, you want to adjust your cell density. Then you're going to incubate overnight so the cells adhere and have normal growth. And then on the next day, you're going to treat your cells with the drug treatment for X number of hours. And again, I say this can be 4 hours or up to 24 hours or even a week. After your experiment's finished, you'll stain the cells with the viability dyes and then acquire on the Celigo. That's pretty much the basic workflow of this whole experiment. All right, so for our part 1 of this training, the plate map is going to contain A549 cells in a 96 well Griner plate. We plated initially 10,000 cells per well. The treatment was with hydrogen peroxide at the maximum dose of 12 millimolar, and then it was serially diluted. So here on the plate map, you can see I have a maximum treatment on the upper left and a minimum on the right and a dose response on the bottom. I prepare my treatments with a 2X, and then I add it on top of the media. I let it incubate for 4 hours on the cells, and then after the 4-hour treatment, I prepare a master mix of my viability dyes. So what's in this master mix? So basically the viability staining is, again, calcium AM, propydium iodide, and Hoechst. Here are the stocks. And this is the master mix that I used for this experiment. I would recommend doing a titration for your cell type and treatment to see if this is the right concentration. If you're interested in a kit from Nexcelum, you can go to support@nexcelum.com. The Celigo viability instructions are also included in this kit. After you've prepared your master mix, you're going to remove the media and then stain your cells with this viability dye by adding 200 microliters of this master mix. Then you'll incubate your cells for 30 minutes, and then you'll image on the Celigo your plate. Okay, so this is basically what was done on this experiment, and then on the Celigo you'll see Viability Application Suite in the drop-down menu. You have the option of these 4 different ways of imaging. Today we're going to talk about the live, dead, and total 3-channel acquisition, but you have 3 other options if you would rather do those other versions. So for the image acquisition, it's very similar to some previous webinars that we've covered in the past. So I'm going to refer you guys to refresh your memory on the video portion of the transfection efficiency or cell cycle. This will show how multiple channel acquisitions can be set up. But just as a step-by-step overview, we'll go over it here. In the Scan tab, you're going to select the Celigo application, Cell Viability, Live, Dead, and Total. And then you're going to navigate on the plate map to a well with a good amount of live and dead cells. Then you're going to set up the live channel for the green illumination with about 10,000 microseconds exposure. Then you'll set up the dead channel with the red illumination for your propydium iodide stain, and the exposure is about 40,000. And then your total channel, you'll turn on the blue illumination at about 100,000 microseconds exposure. Register the hardware autofocus using the blue hooks channel. Then switch over to the live channel again and find focus and then set offset. Then switch over to the red channel and then click find focus and set offset. All right, so you basically have your illumination, your focus set up for all your channels. A reminder here that you want your pixel intensity average to be between 100 and 200, and then the background should be between 100 and 40. This will give you a good signal to noise ratio for your image analysis. And then finally, you'll just select your wells to be acquired and start analysis or start acquisition. So basically, this viability workflow, we've talked about how to set up your plate and then how to acquire the plate on Celigo in the easy method. And then again, if it was a little fast, I highly recommend reviewing the webinars from our website on cell cycle and transfection efficiency. For the rest of the webinar, I really want to focus on the analysis and the review of the results and the plotting of the data for the 3-channel easy method where the channels are pre-labeled. So we'll view and analyze the scans. In the demo users folder, we'll type in cell viability, and you'll see we have 1 scan time, and it was acquired with live dead total 3-channel. It already was analyzed, but we're going to create a new analysis and then select live dead total. All right, so in this Analyze tab, you can see that all the channels and the graphic overlays are pre-labeled live dead total. It's an easy way for you to set up and remember which colors go to what. Now we'll select a well that has a lot of live and dead in it. We want to have a good mix of both. This has a little bit, mostly live cells. Let's go a little higher in the concentration of drug. There, we have a few more dead cells in this image. So let's zoom in on this image and we can see all the cells a little bit closer up. Okay, so for this application, we need to set up the graphic overlays for all 3 channels. So what I like to do is I turn off the channels I'm not currently setting up the parameters for and just leave on. We'll start with the total channel first and turn on the graphic overlay. It's going to outline the nuclei. And the first thing I like to do is select the well mask. It's going to be identifying only objects inside the well area. And then change the identification channel to total. Currently it's set at live. We'll switch over to total. So the parameters now below are reflective to changing objects in the total channel. The default settings are pretty good. The only thing I might check is this separate touching objects. It helps separate these nuclei that are in the lower image. There we go. They're separated now. And then also it might filter out any small debris that is smaller than a nuclei. So 10 is the default. Let's bump it up to about 50. I didn't make any visual changes on this image, but it just eliminates any possibility of small debris. Let's move around and see if anything is not sitting well. It looks pretty good. I'm happy with this. So once you're set with your segmentation for the total, we'll want to turn on the dead image and graphic overlay and turn off the other 2. So now we can focus on setting up the segmentation parameters for the dead PI stained cells. So here we have the blue overlay. It's doing a pretty good job. We'll switch the channel identification to total, and maybe let's decrease the intensity threshold so we can pick up a larger surface area or maybe some faintly stained cells better. And then also we'll do a pre-filtering minimum area requirement of 20 instead of 10. That looks pretty good. I'm happy with that. Why don't we turn on the live channel and graphic overlay, and we'll turn off the dead. So here the purple outline is outlining the green cells. That looks pretty good. We'll change the identification channel to live. The intensity threshold seems to be pretty good. I think we're picking up all the live cells. We might want to just minimize the pre-filtering to 50 so we get rid of the faintly green cells. There we go. Now we're going to save these analysis settings in case you want to use them for another plate later on in the future. You can easily recall these settings. You'd have to go through this all again. Then we'll just select the wells to be analyzed for this analysis setting. So click Analysis and then the plate map, and then click Start Analysis. All right, so the system is going to analyze all the images. You can see that we're looking at the green live thumbnail images. So the numbers are showing up according to % live, and you can see in the top half I have my minimum control, and on the right we have the maximum. So there's a lot of replicates. We can look for consistency and robustness on the top half of the plate. And then the bottom half of the plate is our dose response of the hydrogen peroxide. That will give us our IC50 of this compound. And then for, you can just see the thumbnails are populating on top of, with the data on top of them. And the numbers look pretty consistent with the treatment as expected. But for easier viewing, let's turn on the heat map because that's a little bit easier. It'll color code to the values. So currently we can adjust the maximum to maybe 80. And we'll see that anything that's above 80 and above with color code red, and anything below about 5 is green. So we have our many live cells on the left and not many live cells on the right, and then our dose response on the bottom. It's a good utilization tool for visualization. Now we can switch the data format presented to %dead, and the thumbnail can be switched to the dead by just changing and clicking on these different parameters on the left-hand side. And then there's the total count of cells. So if you had a inhibitory growth factor in there, you could see your total count also adjust. But remember, we're going to be most interested in the percentage of live, so that's taking an effect of the number of cells. All right, that looks pretty good. Now let's just double click on a well that has a middle amount of live and dead, and that'll open up the the high resolution image, and also turn on the graphic overlays. So now you can see the cells are properly identified with the nuclei, and then the color coding for the live and dead. So if a live or dead object was touching a nuclei, it will be counted. So this really localizes the cells count for live and dead. So if there was some green debris or red debris that was not associated with a nuclei, it's not counted, as it is ignored in the data. And the data is presented on the left-hand side. You can see % live, % dead, and live corrected. Live corrected is actually subtracting out any double scored, so it would have a positive calcium and a positive PI. So live corrected is truly the live alone. Okay, so once you're happy looking at your images and your data, we can go back to the main page where the plate map is, and then we can go and export this well level data into a CSV format. Let's just put it on the desktop. We'll call it Cell Viability. Okay. Now if you want to there are a couple of different ways you can save your images for reporting purposes. It's always saved, the computer has always saved your data as is, but if you want to put it in a report or something, you can right-click the scan area on the well. In that particular well, you can save that image set, the live, dead, and total, of the raw images of only that well, if you wanted just that one. Now, that's just for you to put it in a report or something else. Now, if you want to have an image with the graphic overlays and the pseudo colors, green, red, and blue, then you would find this image that you like. So you turn on the graphic overlay, zoom in to where you want to be, find that perfect spot, and then in the upper right-hand corner, there's a word called displayed image, and there's a little save icon to the right of it. So we'll just click on that save button, and now this rectangular area that we're viewing is going to be saved as an image. You can save it as a bitmap, JPEG, or a TIFF file. So this is a nice way to actually capture some stuff for your reports if you're making a PowerPoint presentation and you want to make a representation image of what's going on in your wells. Now again, here's another way you can get the raw data. Just click Export Images on the lower left-hand corner, and this is how you can export the raw images. We'll just populate that on the desktop. Let's go see what the difference looks like between these three. So here we have the viability image with displayed graphic overlays, and then we have the raw images. This is the black and white camera image, and this is the live calcium AM stain. This would be the PI image, and then we have the Hoechst image is the last one. So it's the whole well stitched together. The pseudo colors are not in the raw image. The images are truly black and white. Okay, that looks good. And then next we will, let's look at the viability data. So here is the CSV file we exported. The top portion displays a lot of the information about the plate, the scan ID, the application, the user, the time of acquisition, and analysis. The top portion is your percentages, and then the next grouping down is your counts of your objects. We're going to be focusing on the percentages. So let's copy the area of percentages, and we'll paste this into a template that I've created. Up here in the left-hand corner, let's just paste it as is, because I like to see the data in the plate format, but I also need to transpose it, so we'll copy and paste it into a transposed format so it's easier for me to graph. So now those numbers populate into a graph. You can see we have the three groupings, % live, % dead, % live corrected, and then they are averaged and standard deviations are created down here. So for the min-maximum, these groupings of data here help me create a z-factor. So here's the formula for the z-factor, and this is a robustness factor. The range is from 0 to 1. Anything above 5 is considered robust. We're at 0.887, and that is a very robust assay. You want to have a strong delta between the min-max and a small standard deviation. In this next graph on the right, we have the plottings of our dose response curve for the live. So we've plotted the average and standard deviation for all three. And you can see that the live and the live corrected are sitting nicely on top of each other, and the dead is in the opposite direction, and we have some tight standard deviations. That looks good. All right, so we basically have gone over the assay setup, the image acquisition, and the analysis for the easy method. This is the pre-labeled 3-channel application. Now I want to go over the advanced method where it's 4 channels, utilizing that 4th channel with a bright field image, and we'll also do some gating. So on the left side we have the viability application suite that we saw earlier. Now I want to show you the expression analysis suite is where we're going to find the application that we're going to use next. You have 4 different versions, and we're going to use the 4-channel version, target 1, 2, 3, and mask. where the target 1 is green, 2 is red, 3 is bright field, and mask will be blue. So in this part 2, we're going to have a plate map here displayed on the right. We've got A549 cells in a 96 well, 10,000 cells per well. We've got 2 different treatments, alpha-TOS and staurosporin. I prepare it again the same way as I did before, 2x added on top of the wells with the cells, incubated for 18 hours, and then I stained with the Viability stain mix that we used previously. So to view these images, we'll click on View and Analyze Scans, and we'll type in Viability to pull up the scan. So you can see that I created a title reflecting what it is. It's a 4-channel application. And the first channel was live, the second one was dead, and the third one was bright field, and the last one is the nuclei. And that is what we're going to use as our mask, the nuclei. So let's create a new analysis. And then in the drop-down menu, you'll see these are all 4-channel applications that I could use on these images. I want target 1, 2, 3 mask. All right, so in the upper portion of the screen, you'll see that the channel names are target 1, 2, 3 mask. Not very generic, not very specific to us. So let's change those titles to be more reflective of what we're going to be having in our scan. So we've got green, red, bright field, and blue. And then on the classes, which we're going to use in the gating tab, we're going to score the cells whether they have a positive green stain, a positive red stain, or negative for either of those 2 dyes. So just to help for visual, we'll score what they're called. So positive calcium AM only would be live, positive for both would be dying, and then positive for PI would be dead, and then negative for both, we'll call that debris. So now the advantage of having this 4-channel is to actually help you visualize your cells in the bright field. You can see if there's any morphological changes going on with your drug treatment in addition to your viability staining. So you can see that we have all the 4 channels here displayed, and you can turn them on and off in any combination. You can see we've got some bright green cells and we have some red cells. So what do they look like in the bright field image? Those are looking like a couple of dividing cells. They're going through some cell division, and then we have some dead cells. Looks like the cell is kind of blebbing. There's a bright field image. It's kind of hard to see, so what we can do is we can adjust the background and gain of the bright field channel to increase the contrast of the image. This is just an artificial way for you to help visualize things a little bit easier on the screen, but the image itself is saved the way it was captured. So now you can see just turning up the background provides a little bit more contrast to the bright field image, and it's allowing you to see some more detail. Oop, there's the bright field. That looks good. Okay, so for this application, target 1, 2, 3 mask, we only need to set up the analysis settings for the mask channel. We don't have to set it up for the other 3 channels. So just click on the graphic overlay blue, and it starts to outline the nuclei, the hook-stained nuclei. So we'll just make a slight adjustment to separate these touching objects like we did before. And that should separate those clusters. All right, there they go. And then also we're going to want to turn on the well mask to isolate the analysis to the well area according to the plate specifications. And that looks fine. And then maybe we'll just lower the intensity threshold to pick up those faint cells or increase the nuclei area that we have. And again, we only need to set up the mask channel. We do not need to worry about the other 3 because it basically is outlining the same area as the mask. Okay, so we'll just go ahead and select the Gate tab, and we'll move over to the Gate tab. This is where we're going to set up our plots to help us define our subpopulations, our 4 classes that we want reported. So to begin, you need to select a well on the plate map. Let's pick a control well, C6. The image is now stitched together. Before we were looking at one field of view, one FOV. Now in the gate tab, the whole image is stitched together. So we'll just scroll in and zoom in on our cells so we can see them. At some level, the graphic overlay will appear. The graphic overlay on the Analyze tab was yellow. In the Gate tab, it is this royal blue color. So you can turn it on and off to see your cells and then turn it back on. To start creating your plots, just click this green plus sign. The first plot that we're going to want to create is going to kind of be of a pre-filtering sort, so we can eliminate any small debris or large clumps of stuff. So select the plot type, histogram, from the drop-down menu. It's the first one. And then the plot parameter we're going to use is area. So then all the objects that are outlined in blue will be plotted according to their area. And we can see if there's a good this distribution of our cells. Yep, so we have basically a cluster of cells on the left-hand side between 0 and 300. There's probably a few objects that are really big, and there's one-offs in the, on the right side of the graph. So that's why it's displayed so large. Let's just adjust the graph so we can only concentrate on the histogram peak. So let's change the axes by clicking on that ruler, and let's pick a value between 300 and 600, maybe 500. Select fixed for your axes and change 1500 to 500. Now the displayed graph will shift over, and now we're going to use a min-max gate in the upper bar here to localize the objects of interest to be in the peak of this histogram. So click on the left side of the histogram and then drag your mouse over to the right and then release. So it's a red area that's going over the histogram, and you can see the graphic overlay for those objects inside that area are also turning red. And then there's a few blue ones on the image. They're probably a little bit bigger than the value, so we'll just hold the red line down and drag it over, and that should pick up those cells. And then there's let's see, that looks pretty good. Let's just move around a little bit and see if there's any else. Oh, there's a couple small ones. So those small ones will be on the left side of our splitter, or I mean our range, and so they're small debris. And we don't want to include those, so I think the location of that is just fine. So if we move around and see if we've got our, oh, there's another large one. So let's move the bar over just a little bit, just a bit bigger than 400. There you go. Just hold hold the mouse down on the red line and then drag it. And then the graphic overlay should update on your image. That looks good. So let's call this our total population. This will be the denominator for our percentage. And then also I want to change the color for this class because I would like to use the red color in a different location. So let's pick a color that we're probably not going to use in the next plot that we create. Yellow. Yellow's pretty good, but I might use that. I'm not certain yet. Let's pick purple. Purple's a color I probably wouldn't use for scoring my live dead and total. Okay. Yeah, it's not a very contrasty one, but I know that our histogram location is pretty good. I'm satisfied. Purple's fine. All right, so now let's create our second plot by clicking the green plus sign again. And the source population is our total. The plot type, we're going to use a scatter plot this time. Second option on the list. Okay, and then for the x-axis, we're going to select green mean intensity. It's about midway down. So this is adding up in the outline of the cell object all the pixel intensities and scoring a mean. So we're plotting that value. And then for the y-axis, we're going to do the red mean intensity. Integrated intensity is actually summing up all the pixel intensities, so that can be infinite. We would like to stay in a range, so we're going to stay with the mean. So now we've plotted all these objects outlined in purple according to their pixel intensities of green and red. You can see a majority of the cells are alive, and that's why we have a cluster of them on the bottom half of the scatter plot. To help us locate where we want to put our quadrant gate, let's zoom in on that lower portion of the plot by changing the axes for x and y like we did for the histogram. So let's change the fixed value from 255 down to 50, and then also for the y we'll do the same. This allows us to zoom in on that area of the scatter plot, and so we can properly place our quadrant gate. In the bar in the upper top portion of the scatter plot, click the quadrant gate button and then click on the graph in the quadrant area of 30 and 30 for x and y. So this is basically above background for pixel intensity for both the red and green channel. So anything above these values should be scored a positive for either red or green. Now the colors are defaultedly displayed, but if you want to adjust them, which I do because this upper left hand corner is going to be our dead cells, and I'd really like to use the red color instead of this mint green color. This is going to be our scoring positive for dead cells. So let's just click the down arrow and then we'll click on the red box, and that quadrant is now colored red, and any cells in the image are colored red. And we'll check box negative calcium and positive PI, our dead cells. Okay, so the upper right-hand quadrant is our dying cells. It has scored positive for both the green and the red because there are cells that probably in the treatment are in the process of dying. So let's color code this one orange because it's kind of green, kind of red. Alrighty, and then we'll check box calcium positive, PI positive for dying. And then let's scroll down so we can see the other two quadrant colors. The lower left is what we are going to call debris, anything that has a faint or no signal of PI or calcium AM. This blue color is fine. So let's just check box the last one so it's negative for both colors. I would say the one thing to remember is to make sure you have the checkboxes checked. That's probably the one thing that people call me on a lot in the gating tab, is they forget to check the boxes. If you don't check it, the display on the results will not be showing the data you want. And then on the lower right, we have the live cells. That's where the majority are in this image. It's currently color-coded yellow. Let's change it to a green color. Okay. And I know it's probably not a good contrast color for green on green, but for purposes of the demo video, I want to just show you the concept, what's going on. And then check box the positive for calcium. This is our live population. So we have all four quadrants properly checked and colored. Now what we want to do is change the scale of this scatter plot back to the default values so we can see the full population and where it lies with our quadrant. So you can change the number by typing in or just clicking auto. So the auto should shift it back to the maximum 255. There you go. You can see that our control well is very alive. And you have a few orange ones. They're probably just starting to die. And what we'll want to do is click on another well that has a little bit more treatment and see how the population shifts in the scatter plot, and then also the colors are properly showing up on the graphic overlays. So there we have some dead cells labeled red. Yep, and there we've got some more treatment. There's cells that are increasingly dying. And then we have our maximum treatment, I think, coming up next. Yep, they're starting to get leaky and propydium iodide's going in. And more calcium AM is probably going in as well. So, and then here's our maximum treatment. Pretty much everything is dead. There are a few survivor stragglers, but they're on their way to die. That looks pretty good. So I'm happy with the scatter plot location, the quadrant. So at that point, we'll just click Start Analysis and apply those settings to all the images. The data is displayed. You can see on the left-hand side we have the alpha toss treatment and then the staurosporin treatment. The thumbnail images are of the calcium stain, so you can see that the data also is reflective of what's going on in the images. Looks pretty good. So we had a sharp jump from the first to the second dose. This might be a reflective dose response of something you maybe start with on your first experiment. It'll help you hone in on your next experiment what concentration you should choose. So now you can again change the measurements displayed on the thumbnail images as well as you can also see the total counts. There's percentages, counts, and also intensities for those different classes. And then you can change the thumbnail images as well. All right, and there's the green. All right, and then the heat map. Let's click on a well and open up one of the treated wells so we can see what the images look like. All right, so here we have the advantage again of the bright field image. You can see that we have some cells that are alive, but they're looking a little sickly. So the bright field images just helps show some more of the morphology. Again, we'll adjust the background and the gain so we can see more contrast on the image. That's pretty cool. Yep. And then turning on the classifications for our different classes, you can see how they're scored. And then the features is reflective of their mask, so it's really not that interesting. Okay, so there's a break. Oh, this is the control well. Now that's pretty cool. Now it's easier to see the green when you turn off the green image. You can see that what's scored when you just have the blue channel on. Okay. All right, so let's export this data into a CSV and see how it plots out. All right, so once again, the plate information is the first portion, and then we move into the percentages of our classes, and below that is the counts. We're only interested in the percentages, so we'll just highlight all 4 of those classes and then paste it into a template that I've created. Here are the 4, and then we'll copy again and transform it into a linear format. And then it easily populates into the average and standard deviation columns that I've created. And also you can see now we have graphs for the viability of the alpha toss, which is the left-hand portion, and then the staurosporin is on the right-hand portion. And then the red is the orange is your dying, and the red is your dead. And then the dim debris stuff is very low in number, but we plotted it, and it shows up a lot of near highest concentration. So again, this might be a good first round experiment to figure out what ballpark range your doses should be in. Okay, so we've covered a lot today. We basically quickly breezed through the assay setup and the image acquisition. And then we really focused on the analysis of the images for two different ways of looking at on Celigo. So the easy way would be with the pre-labeled channels for live, dead, and total. And again, you can do just two-channel acquisition if there's a channel that you're not interested in. Or you can go the full method, which is the four-channel way, where you can utilize the bright field image. That's also using the gating tab. Now, the Viability Kit is available from Nexlum. Just email support@nexlum.com. The Celigo instructions for what we just covered is inside that kit. So if you have any questions, just email me or email the support and they'll get a hold of me and we can help you through this. All right, I just want to say thanks for attending and we can open up the forum for some questions.
Thank you, Sarah. That was a fantastic session, as always. We are so lucky to have you. So as Sarah mentioned, you can now, if you have any questions that came up or if based on the material that was covered, if you have any questions on how this might relate to your assays, please feel free to type them into the questions bar. We'd be happy to answer any questions you have. Also, as you do see on the screen, next month's webinar is the apoptosis assay with an XN5 staining. As always, it's going to be on the second Thursday, which is going to be June 11th. All right, so I'll just give people a minute here to put any questions in.
Sarah, I just want to remind people that where I see the viability assay used frequently is, again, they've gone through bright field imaging with proliferation experiments, and then at the end they want to just get an assessment of the viability. So this is a real easy assay for anybody to just tack on any proliferation experiment they have going on.
Great. Okay. I'm not seeing any questions come in. So as Sarah did mention, if you're watching this as a recording, or if you are rewatching this after having attended it live and you have questions that come up after the fact and after we've concluded today, you can always email your questions into support@nexlum.com. Also, and we say this every month, if there is a specific topic or assay or application that you would love to see covered in one of these training webinars, please feel free to reach out to us. We love to know what is important for you and what you would like to learn. So you can always send those suggestions in to support@nexlum.com. Just let us know you have a suggestion for the Celigo user training webinar. And I think with that, we can go ahead and wrap it up for today. Like I said, I don't see any questions coming in. We do want to thank everybody for joining us today. It's our pleasure to be able to provide these sessions for you. We hope that they're useful. And I hope everybody has a fantastic weekend, and we hope to see everybody again next month.
Thanks, Sarah.